Thank you, everybody, for being here for my presentation. Vibroacoustic as a fast diagnostic tool for on-load tap changer. So the first part of this presentation shows how the vibroacoustic method is used as a fast diagnostic tool to easily detect mechanical problems in the tap changers online or offline before they create an outage. The second part will present a real case showing how New Brunswick Power has used this tool to adjust properly an OLTC. So 40 to 50% of failures on transformers come from tap changers and are of mechanical origin. And I have seen in the previous presentation the number of 30%. So here we are close. So 4 studies done by Hydro-Quebec, ESCOM, Canadian Electricity Association, and Australia for 10 years on 3 continents shows the same results. And you can see here, like for example, for Hydro-Quebec, they have the number of 45% failures coming from the tap changers. All the others are from current coils, bushings, cooling system, and others. So this table shows a brief comparison between the 5 existing methods available today. Vibroacoustic method offers the widest detection spectrum. This table is from C-Gray. For example, you can see that overheating and cocking is marked low for vibroacoustic, but is marked excellent for the timing and transition and arcing too. So here you can see the 5 methods: vibroacoustic, motor current, dynamic resistance, dissolved gas analysis, and the thermography. And here you have all the problems are noted here in this part. And in fact, what we can say that the Zensol is able to do these 3 tests in only 1 test. What kind of benefits OLTCs, vibroacoustic testing bring to electric utilities? A total of 14 benefits have been identified. First, it's applicable to any kind of tap changers, applicable online or offline, quick and easy and intuitive test similar to a stethoscope. With vibration and current combined, we're able to detect a large range of potential problems. This forces us to have a better understanding of how tap changer works. And thanks to this understanding, we can detect problems at an earlier stage. And it's excellent in terms of timing and mechanical adjustment. It's also an easy tool to detect arcing contact problems, online only. And we have Hydro-Quebec envelopes, which and in the software, it's easy after to analyze the vibroacoustic. What we need a high sampling time and an unlimited recording time, which is unique in the market. And it's an excellent tool to help the user to decide which OLTC are due for a maintenance operation. So, for example, if you have 20 transformers to maintain in a period of time, you can do the quick test, the vibroacoustic test, very quick with a motor combined, and then after you can decide which transformer has to be opened. And in testing OLTC before and after maintenance, this tool can be used for a quality control. And in testing year after year, trending analysis becomes easy and allows a reduction of maintenance interventions. And of course, our goal is to reduce the transformer failures. So typically, the transition of the diverter switch is done in only 50 milliseconds to avoid overheating the resistance. We are able to listen to all the impact of the mechanism during a step up or step down operation. Here you can see a zoom on the vibroacoustic signal And well, here to here, we have close to 50 milliseconds. And for example, in this here, you have a resistive OLTC type diverter switch operations sequence. So here we are in tap 3, and we go to tap 4 here through all these transition contacts and all the details from this. So of course, this information is important to have from the manufacturer, and then after we can associate it, correlate it to the vibroacoustic signal. And what is important also is that the motor operates between 2 and 12 seconds. So motor drive mechanism, this motor allows the tap changer to move from a position to another. In recording, analyzing the EC or DC current of this motor during the step up or step down operation, we are able to know if the mechanism are forcing or not. And the motor current allows us also to start and stop the recording. It's why what we have developed, it's a recording event. Vibroacoustic diagnostic principle, each operation of an on-load tap changer produces a specific vibroacoustic wave pattern, or what we call a signature or fingerprint, and with a vibroacoustic sensor, which is an accelerometer, not a microphone, we can record this signal the same way a stethoscope picks up a person's heartbeat. And a stable tap changer always shows consistent signatures. Any degradation of the OLTC induces change in the signature. So how we do this recording? First of all, the sampling time. The sampling time is the time interval between two readings, and it's an important parameter to keep in mind. So we use 10 microseconds, so which is a frequency at 100 kilohertz, and this you have a picture of the recording, which we call the tap 4 plus. Here you have an example of good and bad recording of vibration signals. Here we have recorded at three sampling times different, 10 microseconds, 100 microseconds, and 500 microseconds. So exactly the same event, what is this event? It's a vibration of a ball bouncing on a plate. So here you have 3 recording at the 3 sampling time different. And now in next slide, you will see a zoom of this part. So what we see, well, so at 10 microseconds, it's why it's in green, you have a clear signal, which is very clean. At 100 microseconds, we have a broken signal. You have the information, but it's broken. At 500 microseconds, it's totally broken. So in fact, at 500, you see nothing. 100, you start to see, and if you want to see clearly, you need absolutely to have the 10 microseconds. And on top of this, you need absolutely an unlimited record time of recording. This is the duration. So what we need an AC current clamp or a DC current clamp, 3 accelerometers, the recording system with the software associated. And what is important is that you must have your 10 microseconds for the sampling time. The 16-bit, it's also an important parameter because it's the quality of the signal and unlimited recording capacity. And of course, you need to start your event recording and stop your event recording. So here it's some examples of connections. We use a tab glue that, first of all, we have a tab base that we install on the close to the tap changer. Here, the accelerometers, a special cable that we call microdot, then a BNC, a standard BNC. Exactly the same for the current, EC or DC, and the connection between the tap 4 and the computer, which is done through the USB high speed. We have also this system is used for the online monitoring for the transformer for the tap changer. So exactly the same connections. And here, the first step, we need to identify the tap changer, the motor drive mechanism in the control cabinet. Well, usually I show a video or how to do this. Next step, the accelerometer should be installed of the closest possible location to the transition mechanism. And here you can see the aluminum base, which is glued. So first, the aluminum base is here. We have the glue. We put it at the best location. Sometimes it's at the bottom, sometimes it's at the top. It depends. So it's good to have a good knowledge of your tap changer in your transformer. And then the accelerometer is screwed into that base. So here we have a comparison between the three methods of installation of the accelerometers, and in the previous presentation, they use the magnet, and here you can see. In fact, I have received a lot of questions regarding the attachment methods and why we use the glue instead of the magnet, which is easier to use. So to answer these questions, we have done recently the comparison of the three accelerometers attachment methods. And here you can see the beeswax on the top, the magnet on the right here, and the glue. In fact, so here you have the magnet. Here you have the beeswax. So in this case, we use for the beeswax and the glue, you are obliged to use what I have shown, this tap base. And so in fact, we have done the recording of these three signals. We have in our tap changer, we are able to put, as I told you, three accelerometers. So it was easy after to compare exactly the signal produced by these three recordings. But in one recording, we get the three signals. So this graph shows a zoom of the impact section of the recording. So in fact, in the previous one, we have this. We have done a zoom in the next slide of this part. And so of this signal from the beeswax, this signal from the magnet, and this signal from the glue. And this is what so this graph shows a zoom of the impact section of the recordings. On the left, you can see the raw data. On the right, the calculated envelopes for the same data. And next slide, we show the detailed analysis. So these are the results. So in orange, you have the beeswax signal, the magnet in black, and the red is the glue. So this graph shows the result of the three attachment methods superposed, and we see clearly that glue and beeswax are identical. So for example, if you come here, you can see the red and the orange signal. So the red is the glue and the orange is the beeswax. So they are really almost the same. But for the magnet, the amplitude of the signal is drastically reduced, that you can see on the other two methods. It's totally the same, and for the magnet is absolutely reduced. So in fact, you have three impacts that are totally reduced in their amplitude. And the top of this, we have here an additional impact is introduced by the magnet. So even if magnet is convenient, it has two major problems: the reduced bandwidth of the accelerometer signal, and the fact that we lose the location of the accelerometer for the future test, which would negatively impact the analysis of trends. So I think with these three, and these tests have been done I have seen also a publication from B&K, which is a manufacturer of accelerometers, showing that accordingly to the method of attachment of the accelerometers, you are going to get different bandwidth for the quality of the signal. So in fact, it's why we are using the glue for the attachment. It has a lot of benefits to do it. The magnet is, well, it's easy, but it's problematic. So here you have an examples of accelerometers installation. So in fact, as I told you, you have to look for where is your tap changer, like here you see, and then you try to put close to the tap changer, and the part of the diverter transition. Examples of current clamp installation. For online test, we record operations of 1 or 2 taps, step up and step down, and tests are performed in such a way to minimize the impact on the customers. And for offline tests, we record all taps to get a reference. So on the left, you can see the raw data with the envelope superposed. The Hydro-Quebec envelopes have been patented by Hydro-Quebec in 2001. And on the right graph, you can see the envelopes for the current here on the bottom, and the high frequency on the red, and low frequency envelopes. So why envelopes? Because it simplifies the signal. We get the shape of the signal, and we can focus on variable impacts only, and it's easy to analyze and easy to compare, exactly like what we have done with the magnet, the glue, and the beeswax signals. And every tap changer has a specific sequence of operation that can be identified in the envelopes. So in fact, here we have the startup, and here you can see in blue the motor current, then the high frequency envelope in red, and low frequency in green. And this part is the changeover switch. Here is the diverter switch, a contactor, selector switch, which is a silent, a new diverter switch. Then here you have the breaking section, and finally the post operation. So depending on the model of OLTC, different signatures can be obtained, which are characterized by the specific operation length, number of peaks, shape of the current, amplitude of the impact, and so on. The sequence of operations associated with an OLTC is described in the operation guide provided by the OLTC manufacturer. So usually what we try to do, even if this information, you can have 300 pages, what we are looking for are the timing events, the timing transition, and also the principle of how the tap changer is operating. So here you have a typical processing with OpenZenTap software. So here, first of all, we have to succeed to get the raw data properly. Here you have the current, here the vibration, and the diagnosis can be made in 15 minutes for an online test and 1 hour for an offline test. Why? Because like when you get these raw data, well, in few milliseconds, you get your envelopes and you get an Excel report which can focus on specific test, maybe problematic test. And here you can see an off-site deep analysis. So we analyze the Excel report produced by the software. We have also, thanks to the high frequency and low frequency envelopes, we can be able to determine if we have a problem of contact wear or not. Thanks to envelope, also we are able to analyze this, and quickly we can detect problems that I can show you in the next slides. And we have a database where what we call, we have OLTC references signatures, and we call these diagnostic cards. Here you have an example of wear of contacts. done Walter Schultz on an EVB UZ ERN. Here it's a severe wear of contacts. So before the intervention, more than 60% of differences between the high and low frequency. Here I can show you, for example, here you can see the green, which is the low frequency, and the red, which is the high frequency envelopes are different. And after repair, after the intervention, we can see less than 20% of differences between the high and low frequency. So immediately, so when it's a good indication, the high frequency and low frequency envelopes are a good indication for the wear contacts. You have also an example of poor lubrication. Well, here you have an example of a motor forcing. The section of the curve shown by the arrow is supposed to be flat. Here, when it's flat, so this means that you have no problem with the motor current. Here you have an example of asynchronism. These tests show an example of asynchronism of the switching operation. In normal condition, the switching operation should occur before the current stops flowing in the motor. In the case illustrated on the left, the switching operation signal is delayed by 120 milliseconds after the end of the current envelope. As it can be easily observed, this kind of issue doesn't require the use of a reference signature, and the asynchronism can be detected immediately. Here you can see the end of the current is here, and the transition has occurred 120 milliseconds after. So this is not normal for this kind of tap changer. And so the intervention in this case consisted in coupling the drive motor and adjusting it so that the switching operation could occur before the motor current drop. So the figure on the right represents the normal condition of the mechanism after the repair. So you can see that how it has been adjusted. So now we are sure that the current is finished, but the transition happened long time before. So here is an example of arcing contact. In this picture, an example of arcing contact is presented. Two tests have been performed on the tap number 10 of the same tap changer. One test has been performed offline, the red curve, so this one, and the other one online, so the black curve. By comparing the two signatures, a big difference in the maximum amplitude can be easily observed. In fact, the maximum amplitude of the offline test is 8G, while the one of the online test is 35G. So the image on the right shows the superposition of the two signatures through which is possible to observe the presence of an extra peak in the online test. And this extra peak represents the arcing contact phenomena. Here you can see, the offline and online are exactly the same, except at this point. So in fact, we are using in this test the capacity of the isometer to detect arcing problems. Here, it's an example of time impacts and timing association. During this presentation, I told you that in the manufacturer book of the tap changer, you must look for this information, which is the timing and the principle. So here, so what we have to do after, and if you are able to do this, it's really nice, because after you have, for each impact, you are able to associate the contact, the diverter transition. So here it's the other examples of abnormal inrush current, comparison of the two inrush currents between two transformers, same type and totally new, and this has been able to adjust properly the inrush current. Or in fact, it was in some tap changers, you have some relays that control this inrush. And here you have a normal current, forcing current here, exactly the same. On top of this, you have an oscillation which is not normal. Here is an example of motor drive current analysis. Throughout the years, we can notice some malfunctions. So here, for example, you have here in 2014, 2016, and here you have some differences at the end of the current and also during the plateau. And here in 2014, the same, and 2016, in 2016, the inrush has disappeared. So there is some wrong. We can notice some malfunctions. And our other examples of inconsistent setup connections. It's why we recommend strongly to when you put your current. You must absolutely put like an identification for the wire. So this way, next in next test, subsequent tests, you can go exactly at the same location for the current. And also another aspect, the analysis of the braking mechanism is an important part of evaluating the health of an OLTC. And this is done by observing the appropriate portion of the recording current and the corresponding vibration measured by the axiometers. So now the challenge, it's how to facilitate the compression of a vibroacoustic signature, and several mechanisms are operating at the same time. So one way to address this challenge is to analyze simultaneously three recordings: the vibration, the dynamic resistance measurement, and the motor current of the tap changer in action. So equipment needed, we have developed a new accessory that we call tap DRM. Here you have a tap 4 plus, and this is done on a normal transformer, so you don't have to open it. It's an easy test. Of course, it's an offline test. And this is some example of a DRM recording. I'm sure that you are familiar with this curve that shows the transition, the contact transition. Here you can see the contacts while they move. And here you can see the correlation between the electric schematic and the mechanical movement. And here you can see the correlation between the dynamic resistance on the top, the vibration signal in the middle, and the motor current during the transition. So in fact, thanks to the dynamic resistance, you are able to understand exactly the vibroacoustic signal, and then after so this test is done offline, and the goal of this to correlate these two signals is to learn the vibroacoustic signal. So this way, after you can do your test online and you understand exactly what happens in the tap changer during the transition, because like in the beginning of the tap 4, it was in 2008, 2009, the users they have only the vibroacoustic and the motor, but a lot of times they do not understand the vibroacoustic signal, what is this impact and why it's here. And so it's why in 2015 we have worked on the correction of the DRM correlated to the vibroacoustic. So in this way, so even like a beginner is able to understand the vibroacoustic signal. So here we had a high-speed camera. We are all able to see the transition and correlate the image to the DRM and the vibration signal. So here you are able to see, and here we are able with Vibroacoustic to see, to listen, and here we know exactly what happens inside thanks to the electric model. Here we have other examples of MR and ABB OLTC. So here it's an example of installation done at Hydro-Quebec substation. You have the tap DRM, tap 4 plus, the current clamp, and as I told you, like an identification, which is important because this way we are going to compare the signals exactly at the same location and to avoid bad comparisons. The accelerometers, so the tap base is always here. So when you do your test, you screw your accelerometers. When you have finished your test, you remove your accelerometers, but the tap base stays there during a lot of years, and it works perfectly. Here is an example of typical recording. Looking at image on the left, the total operation time shows 6 seconds. So thanks to the current. In the bottom left here, looking at the image on the right, the resistant transition and the corresponding current drop are highlighted because the resistance is, in fact, you applied the Ohm's law, you have V and you have the current. And so from V and I, you are able to calculate the resistance during the transition operation. And we can also see the vibroacoustic signal of the diverter shown by the accelerometer's curve here. So shown are several step-up and step-down operations recorded in a single test. Look at the arrow showing that voltage or current are not interrupted. Such tests are performed for tap positions where we suspect that there might be a problem. So we go up and down this tap position to gather data to troubleshoot the problem. So this way, if there is something wrong, you will see it clearly. You will see like a broken signal. Here, and we see an example of DRM analysis, and here it's the zoom section, the previous slide. So this is an example of action plan to elaborate a predictive maintenance for transformers with tap changers. Step 1, establish your transformers list with OLTC to monitor. Step 2, for each transformer, do a complete test to get a reference. So we have, so this is done offline. And we have developed a checklist to be able to do this very quickly and properly. Then step 3 is to produce a complete report analysis for each tap transformer with the tap changer. We have developed also a template for the report analysis, which is produced automatically. And according to the diagnostic results, you can establish your maintenance plan for each transformer. And after, you can do a vibroacoustic, periodic vibroacoustic test offline or online. So this is the second part of my presentation. I hope I'm okay for the time, Randy. Okay, so here it's
yeah, everything's fine, Fouad. Everything's fine.
Okay, everything's fine. Thank you. So here the second part has been produced by Christian Noel, which is a professional engineer in a new Brunswick Power. And the first presentation has been done in 2023. So here I'm doing just his presentation. So this test has been done in Caracat on the transformer T1. So it was a maintenance done on the LTC maintenance MR type M3, and they have done a vibroacoustic with the DRM performed before and after maintenance. So this maintenance was performed on our Caracat T1 transformer. This transformer is equipped with a Renhausen type M3. So in general, there are two types of tap changer: compartment or box type and in-tank design. In our case, this LTC is an in-tank design. Almost most of our in-tank design LTCs are 3 separate phase models. We do have a few delta configuration. A delta configuration has a cylinder with two diverters, and the other is a regular cylinder with a single diverter. So in fact, here you have the two diverter. No, sorry, here you have the one, and there you have two. So timing between the motor drive and the diverter assembly is adjusted using the shaft connections between them. In this case, we installed two vibroacoustic sensors, two on separate walls near the diverters and located about 18 inches from the cover. So in fact, we use only one, but here they were not familiar, so they want to compare these two locations. And to answer this question for why the two locations, so you can see that the two locations give exactly the same informations. So generally, a tap operation on this style of tap changer will include the following steps. One of the selector contact is leaving the previous tap position stationary contact. This moving selector contact is then connecting to the next tap stationary contact. The energy in the diverter energy accumulator is released to switch the load current to the next tap connection. On this graph, we are seeing the sound made by each operations being captured by both vibroacoustic sensors, and also the motor current captured by EC clamp on the CT. So when adding the DRM information to the previous graph, we can then confirm that when exactly the diverters are switching the current, it helps understand the information provided by the vibroacoustic sensor. So here you can see the voltage, the V, DRM, and here you can see the Y. And the signal was a little noisy, but in fact, we have the good information. And in fact, with the V and I, you are able after to draw the DRM, but the DRM has not been presented in this, but we get it through the voltage and the current. So this is the before maintenance. So the result shows are from before the maintenance. We are seeing all three phases side by side. So here you have phase A, here you have phase B, and here we have phase C. We are seeing side by side. From this information, we can tell that A phase is not operating in sync with B and C phases. A phase is likely the single diverter, where B and C phases are associated with a double diverter switch. So you can see clearly that here it happens during if you analyze just the motor current, you can see that this one happens quickly, but when you compare the other two, you see, so the B and C are synchronized, but not A. So tap up before maintenance, our test plan calls for testing all the tap transition going up and also back down. In this up operation, we're seeing that A phase is operating earlier than B and C. So the B and C operate here and the A operates here. But in the down operation, so now it's before maintenance also, tap down. But in the down operation, we are not only seeing that A phase is operating slightly later than the other two phases. In fact, A phase is operating after the motor current is interrupted. So this is exactly the case of I told you in my previous slide. You see, the motor current has finished, but the A phase is operate after. So the timing of this diverter is at the limit where it could possibly not operating during a down operation. So this would result in a phase being on a different tap than the other two phases. So in fact, they have to do something. So this is after maintenance. This graph is now showing the acoustic signatures and DRM information recorded after our maintenance, and we're seeing A phase operating now around the same type time as BNC phase, so around 4 and 20. So here you can see that the A phase now is not operating after the end of the current, but during the current. And this is, but the big improvement can be seen on the down where A phase is operating well within the runtime of the motor now. So this aligns what was seen with BNC. So just to review the before maintenance readings, showing the difference in timing between A phase and the other two phases. So it's exactly like that. Was before maintenance. So what we have in the beginning, you see, and now all is adjusted. So the after maintenance results now indicate the timing between all three phases is now better adjusted. The selectors and diverter operations are now more in synchronization. Is what we see here. So they are all well adjusted. In not showing the down operation, but the timing was the same as the up operation shown on this slide. So in summary, in conclusion, Zensol Tab 4 can give a good indication of the timing between diverters. When time allows, it can be used before and after maintenance to validate the LTC is operating properly after intervention. So, and as we are gaining more experience with the information provided by Tab 4, we could use offline acoustic measurements to focus prioritized maintenance on specific units. So, Randy, I think I have finished. So if you have some questions.
I do. Drew mentioned that in his presentation, if I read that slide correctly, that 30% of transformer failures are caused by online low tap change OLTC failures. Is that a good estimate?
Well, your previous presenter has given the number of 30, and like Hydro-Quebec, Australia, and give 40 to 45%. For example, in the beginning, I have shown 45% for Hydro-Quebec.
Yeah,
and this number has been published.
Right. Is there a cost difference, a relative cost difference between Vibro-Acoustic and other traditional testing methods?
But in fact, the problem is that you don't have a traditional method testing for the tap changer. It's as I told you in the beginning, you have the Vibro-Acoustic that has been developed like 2000, maybe 5, 6, 7, and then the motor current is the old method. But it was only just like the motor current and the GA, the DGA, the dissolved gas electrolysis. So in fact, it's why we are pushing the Vibro-Acoustic, the DRM, and the motor combined. So all these three can give you like a good pictures on how your tap changer is working.
Is this kind of testing more suitable for older transformers or newer transformers also?
It's any kind, old and new. Like for example, for the old, well, you can see if the adjustment is consistent or not. So it's I compare this like the electrocardiogram. If you are old, this means that you have not the right to have your electrocardiogram. But so you have only, if you have only a young guy, you can have it gives good information because you have a typical signal, which is clearly shown, that I have clearly shown in the presentation. And if this is our reference, and most of tap changers work according to these signal, to these typical signals. So in fact, after it's easy to do. It's like it always I come to the heartbeat. You must have like a typical recording, which is your reference, and from this, and for any tap changer, it's exactly the same.
Where are these recordings, where are these results stored? Is it in a database that the client has? Or do you store that information for them, or where does that take place?
Well, in fact, the recording are in what we call in a binary form. This is the first step, as I have shown, like on a typical processing slide. And then after you get what we call the envelopes, and you can store the envelopes in the database if you like. And then after we get we have a software which is able to handle all these databases.
Okay.
And then so after you can compare easily between years and years and some typical recording.
Okay.